An integer n cities labeled 0 through n, 1, a list edges where each edge is u, v, w, meaning an undirected road between u and v of length w, and an integer distance threshold. Rule: roads are undirected. For each city count how many other cities lie within the distance threshold using shortest paths. If there is a tie on that count, pick the larger city number. The city index that minimizes the neighbor count within the threshold, breaking ties by largest index. In the example, 4 cities are linked by those edge lengths. With threshold 4, city 0 reaches 2 other cities, cities 1 and 2 reach 3 each, and city 3 reaches 2. The minimum count is 2, tied by city 0 and city 3, so we return city 3 because ties break toward the larger city number. Fix one city and a distance cap. Along shortest paths, only cities within that cap count as neighbors. It is like a range limit, who is still inside the bubble. So the mindset shifts from one shortest path tree to a full distance map. For each source city you count how many destinations fall under the threshold, using those shortest distances. One way to fill that table is FloydWarshall. For each intermediate k, ask whether routing through k improves the best distance from A to B. When the sum of 2 legs beats the old estimate, you update the matching cell in the all pairs distance table. Finally, treat those counts like a scoreboard. The answer is the most isolated city, meaning the smallest count. If 2 cities tie, the problem wants the one with the larger index. We assume you already know FloydWarshall, the triple loop that relaxes every pair I, j through each intermediate k. Here we use it to build an n-by-n table of shortest path distances from the roads, then for each city count how many other cities fall within the distance threshold, and return the city with the smallest count. Ties go to the larger city number. Start with infinity off the diagonal meaning unknown distance, and 0 on the diagonal because each city is 0 steps from itself. Relax each undirected edge in both directions. If the weight is cheaper than infinity, store it as the current best guess between those 2 cities. The triple loop tries every intermediate city k and updates each pair I and j by comparing the direct estimate with a path that goes through k. Finally scan each row of the finished table. For city I, count every j not equal to I where the shortest distance is at most the threshold. Tally city 0, the row shows 3 to city 1 and 4 to city 2, both at most 4, 5 to city 3 is over the threshold, so 2 neighbors. Tally city 1, 3 to 0, 1 to 2, and 2 to 3 are all within 4, so 3 neighbors. Tally city 2, distance 4 to city 0, 1 to city 1, and 1 to city 3 are all within 4, so 3 neighbors. Tally city 3, 2 to city 1 and 1 to city 2 qualify, 5 to city 0 does not, so 2 neighbors. In the example, city 0 and city 3 each have 2 neighbors within 4, so we return 3 because ties break toward the larger city index. Let n be the number of cities and e the number of roads. FloydWarshall runs in order n cubed time in the worst case because of 3 nested loops over k, I, and j. Filling direct edges is linear in E but the triple loop dominates at the problem sizes here. Space is order n squared for the all pairs distance table, only a few extra counters are needed besides that matrix. Main routine, nearest city given n, the edge list, and the distance threshold. Allocate a square distance table and fill it with a sentinel meaning not reachable yet. Loop over every city index to set the diagonal. Distance from a city to itself is 0. Loop over each undirected road as U, V, and weight W. Record the road from U to V if it improves the current estimate. Do the same from V to U because the graph is undirected. Outer Floyd loop, try each city K as a possible intermediate hop. Inner loop over source row I. Inner loop over destination column J. Relax the path from I to J by comparing the direct table entry with going through K. Track the champion city index, initialize best to 0. Track the champion neighbor count, initialize best count to infinity. Second pass, loop I again, this time to count neighbors within the threshold for each source. Reset the per source counter to 0 before scanning that row. Inner loop over J, every possible destination city. If J is not I and the shortest distance is within the threshold, J counts as a neighbor. Increment the running count for city I. If this count is strictly smaller than the best so far, or ties with a larger city index, update the champion. Write the new best neighbor count into best count. Write the new best city index into best. Return best as the problem answer.